In this video we will look at a common standard type of capacitor problem. You're given the following RC circuit. This switch has presently got a 2-pole switch. It's set here at point B, and at point B the capacitor has been discharged, so there's no voltage on the capacitor, and then at some instant, which we'll call 0, the switch is switched from point B to point A, connecting up the battery and beginning to charge the capacitor. The first question is, when you connect the switch to this place and eliminate that, what is the RC time constant? Well, we need to find the resistance and the capacitance of the circuit. Tau is equal to RC. The resistance that the battery sees pumping the charge to the capacitor is this 2K ohm resistor right here. So 2K ohms. The capacitance is 10 microfarad. 10 times 2 is 20. And a K ohm times a microfarad is a millisecond. So that's the time constant. In 5 time constant, the capacitor will be fully charged. So in 100 milliseconds, or a tenth of a second, this capacitor will be fully charged to 10 volts. What's the next question? What is the initial current going through the 2K ohm resistor when we begin charging the capacitor? Well, let's see. There is initially no voltage across here. There's 10 volts across the battery right here. The sum of the voltages around a circuit must always equal to 0. That is Kirchhoff's voltage law. So we're stepping from here to there. That point is now at 10 volts if we called this 0 volts. This point here is at 0 volts because this whole wire is an equipotential surface. We said that there is no voltage dropped across this capacitor. So this point is at 0 volts. That means that point A right here is at 0 volts. So we see across the resistor is 10 volts at this point, no volts at that point. The drop is 10 volts. Volts. Now, to find the current, we need to take that voltage and set it equal to IR. So I is VR over R, 10 volts, 2K ohms is 5 milliamps. That's the current initially flowing through the resistor. What is the maximum voltage across the capacitor after charging? Well, once this circuit is fully charged as capacitor, the capacitor acts as an open. Now, some people say, well, it always looks like the battery. Well, for this simple circuit, that's true. But in more complicated circuits, it may not. There may be other things in parallel to it or other paths. What you want to do is simply act like this capacitor is a broken wire and find the voltage from that point to here. So no current can flow this way anymore. Now right now, if no current can flow this way, then that means there's no current flowing through the 2K ohm resistor. So there'll be no voltage dropped across the 2K ohm resistor. That means that we step up 10 volts, we no longer drop anything. So this now becomes 10 volts. I'll change my pen. So this is at t goes to infinity. That makes this point here 10 volts. This is all now broke out because it's an open circuit. This whole place here all the way across is at 0 volts. So the difference across the capacitor is 10 volts minus 0 volts, or 10 volts. So if you left it for about 1/10 of a second, and you had a voltmeter across it, you'd measure 10 volts. Now, if you know the maximum voltage, you could be asked to find the maximum charge on the plates. So what's the maximum charge on the plate? Well, Q is equal to capacitance times the voltage, and so we're looking for the maximum charge that occurs when you have the maximum voltage. We have 10 microfarads times 10 volts is 100 microcoulombs. Now, they might ask you a more complicated question. What is the voltage 15 milliseconds after the capacitor begins to charge? This is more complicated because you have to know the formula. The voltage across the capacitor is equal to the maximum voltage it can reach times 1 minus e to the minus t over tau. So it'd be 10 volts, 1 minus e to the minus 15 milliseconds, milliseconds, divided by 20 milliseconds. So we actually have to punch that. We'll need a calculator here. And we get that it's 5.28 volts. And make sure that you're always careful to realize that it's important that the units in the time are canceling the units in the time constant. If the time constant's in hours, then the time here has to be in hours. They have to be in the same units. The exponent of an exponential must always be unitless. Now it says we're going to done the charging, we're going to do a discharging point. It says, let's solve the problem for the discharging. So in discharging, now we're going to come up here and we're going to clear my diagram. So now we're going to move it back to point B. And in this time constant, we see that the 2K ohm resistor is no longer in the circuit, nor is this battery in the circuit. What's in the circuit is the 6K ohm resistor and the 10 microfarad capacitor. So to calculate the RC, we need this capacitance and this resistor. So tau is RC, 6K ohms, 10 microfarads. So tau is 60 milliseconds. That's a much longer time constant in the discharging because it has a much larger resistance. Now they ask another question. They say if the originally had 4 volts, what is its voltage 20 milliseconds after the switch is thrown to position B and starts discharging? Well, again, this is one where you got to know this voltage formula. So the voltage in the capacitor is equal to V max, but this time it's just e to the minus t over tau. So the capacitor voltage is 4 volts because that's what it initially started with, which was its maximum voltage. And then it's e to the minus 20 milliseconds over 60 milliseconds. And again, we need a calculator. And we find that's about 2.87 volts. What else could they ask you? They could ask you to find, now that you have the voltage, to find the energy in the capacitor. They could ask you to find the charge in the capacitor. If you knew this voltage, then you know the voltage across the resistor. They could ask you to find the current in the circuit. So these are the important things, but all the stuff that we've studied previously about circuits is still true, and you can still be forced to use that information to analyze the circuit. So you want to understand the RCs in context of the other skills we've learned previously on DC circuits. Okay, I'll see you on another video.